and how to balance redox reactions in acidic or basic medium, and also how you can balance redox reactions using the oxidation number and the number of electrons. Okay, so this is a setup of a galvanic cell. Now, this is incomplete. So here you have two species, and these two species or elements. So these two, they have different reduction potentials, means they have different reactivity. So there is one which is more reactive and the other one which is less reactive. The one which is more reactive usually loses electrons. The one which is less reactive, it's the one that gains electrons. So you get to these two species. Now you get pure metals of these two species. Then you immerse them into solutions of similar metal. So if you get, let's say, iron, then you have to put this pure metal in an iron solution. Then if you get on the other side copper, so you get copper metal, you immerse it into a copper solution. So the two pure metals, they act as the electrodes. So we call them electrodes. So the two metals are called electrodes. Then you get these two electrodes, you connect them through a wire. So it can be a copper wire, zinc metal, but the best wire would be the one that has good conductivity of electricity, or that conducts electricity efficiently. So you connect them, then you put the solutions in beakers. So you put this in the beaker and this in a beaker. So you can see the two metal bars, they are separated. So when you put them and connect them through a wire, so electricity or electrons will start moving from the one which is more reactive to the one which is less reactive. But what would happen here is, so the one which is reactive, when it loses electrons, it becomes an ion. So it will move from the surface of the metal and go into the solution. Then the one which is being reduced will be moving from the solution and get deposited on the metal after receiving the electron. So if you are going to write an equations of what's happening on each metal. So the metal that's losing electron, it will start as a neutral atom. Let's say sodium, right? Let's put sodium. But in most cases, we rarely use sodium as an electrode in a galvanic cell. So we can use, let's use zinc. So we have zinc, neutral zinc, and when this zinc loses an electron, it becomes the zinc ion. So it has lost one electron, you put a plus, but usually zinc loses two. So 2 electrons plus 2 electrons. So we have zinc with a 2 plus, then plus an electron. This is what's happening on the side where it's losing electrons. Then on the side where it's gaining electrons, so you start with the ions that are in the solution. So we have, let's say, copper 2 plus gaining electrons. So this will be equal to copper metal. So if you look at what's happening in the solutions here, the one which is losing electrons, the ions are going into the solutions. Then the one which is gaining electrons, the solution, the ions are getting deposited on the electrodes. So eventually, yes.
Yeah, I have a question. Are you writing what you are saying?
Writing.
Yes.
Yeah, you're supposed to write what I'm saying.
Like,
I
is
was
it
just
showing on the
explaining.
screen?
No, no, no,
It's
no,
hard
no.
to
It's
say.
not showing
Yeah,
on
it's
the
hard to
screen.
say.
It's not. It's not. Okay.
Like just
So
a
I was just
suggestion.
giving a
You're
scenario. I wanted you
explaining.
to understand why we need the sort bridge. So
Yeah, but
now
some
when
of
you
us
look at if
we are visual learners, so the way you're explaining, we are not understanding anything. At least if
you're not
you are right.
understanding anything, but you can see the galvanic cell, right? On the
Yes,
screen.
yes,
Yes, sir.
yes.
Yes,
Okay.
sir, we can.
Okay, so you have the side where there is manganese oxide, right?
Yes.
The other side there is
Yes, sir.
iron too, right?
Mm-hmm.
Okay.
Yes, sir.
Yes.
Yes.
So manganese will reduce oxidize iron metal, right? So it means electrons, they will move from iron to manganese. So when electrons move from iron to manganese, it means you're going to have the iron metal, this iron metal will start losing the ions on the surface. So the iron metal will start losing ions, ions or ions into the solution. So eventually, this side, it will become positively charged because you have a buildup of positive charges on the ion side. And where it's been reduced here, so these manganese oxides, they'll start depositing on the metal. So the charges here, the positive charge will reduce. So you end up with a negative charge on the side which is being reduced, and a positive charge on the side which is losing electrons. Now, because of the charge development, eventually electricity will stop flowing through the wire because current, it's just electrons moving, and electrons, they are negatively charged. So they would rather interact with the positive charge that has developed in the cell rather than going to the other side. So to bring neutrality, to neutralize the charge, in the cells, we add a salt bridge. So you've seen the other setup here on the right, where they've put the salt bridge now. So in the salt bridge, let's do here. In the salt bridge, you're completing now the circuit. And in the salt bridge, what you put here is what you put here is potassium chloride or potassium nitrate. The purpose of the salt bridge is to neutralize the cells or the half cells, the charges in the half cells. So what it does, if you break potassium chloride, you will get in the potassium ion and the chloride ion. Potassium, right? So chlorides, they are negatively charged, and the potassium is positively charged. So the potassium ions, they will migrate to the side where there is a negative charge to neutralize the charge, and then the chloride ions, they will move to the side where there is a positive charge so that they neutralize the charges, the positive charge. So thereby, there will be neutrality in the cells. So the charge here will be 0 on this side, and the charge here also will be 0 because of migration of the ions in the salt bridge. So if they ask you the purpose, what's the purpose of the salt bridge? So the salt bridge just helps to bring about neutrality in the cells. Now, what you are seeing here, where you have the electrode in the solution, in its solution, another electrode in the solution, you have a salt bridge, and you have an external wire connecting the two electrodes. So the whole component, this whole component is called a cell. This whole component is called a cell. Then, if you just consider one side of this cell, let's say we consider just the side or the compartment where there's a metal that's losing electrons, then that half is called the half cell. The other side also is called the half cell. So the side, the half where you have the metal that's losing electrons is called the anode. Is called the anode. Then the other half cell where you have the metal that's gaining electrons is called the cathode. The cathode. You have heard this from batteries. You say, no, there's the cathode and there's the anode. So that's how it come about. So you have oxidation occurring at the anode, and the reduction always occurs at the cathode. Now, if you want to find the cell potential of this cell, or how much electricity this cell is going to give us, if I want to measure how much electricity this cell will give us, I'll use an instrument called a voltmeter. So the voltmeter will help us to measure how much electricity is produced by this cell. And what the units for that will be read on the voltmeter will be voltage. So you just insert a voltmeter in between the wires here. And then as the current is passing through it, the current times the resistance, which is in the voltmeter, will give us the voltage.
Sir.
Yes.
Like, can you have like something to show like what you are saying, because we are not able to understand. Like when you say you put your wires in between here, where like
Okay.
it's not showing anything.
It's not okay. You have seen on the galvanic cell here, right? On the screen.
Yes.
Okay, you have seen where the voltmeter is, right?
Yes.
Okay. No, thanks for that. Okay. So, it's unfortunate that the classes are online. So, I know learning is visual, so it will be a bit challenging for us. But yeah, so I appreciate your help. So if you don't understand anything, please let me know as soon as possible so that you're not left behind. Okay, so this is a voltmeter here. So what the voltmeter is measuring is the potential difference between the two cells or the two electrodes, or it's measuring the pull of volts. So we can also convert joules to coulombs, volts to joules per coulombs. So the amount of work that's required to move one charge through a point, which is the joules per coulomb. Now, the problem with using a voltmeter for measuring voltage is that since in the voltmeter you have a resistor, so that resistor will lead to loss of energy because it will eat up as current is passing through it. So you won't be able to measure the actual cell potential of the cell. So to avoid this, there is another instrument that's used, which is called a potentiometer. a potentiometer. A potentiometer. Do we have a potentiometer here? Potentiometer. Okay. So just imagine the voltmeter as a potentiometer, because it also set up just the way the voltmeter is has been set up in this figure. So a potentiometer measures the potential difference between 2 points or so. But this one doesn't have a resistor, so it won't lose energy in form of heat when measuring the potential difference between the 2 points. So the potentiometer will give you a more accurate cell potential as compared to when you use a voltmeter. So most cases, they use potentiometers for measuring the cell potential instead of the voltmeter, but they are more specialized voltmeters now that don't heat up much, so you don't lose a lot of energy. So you'll be able to measure the cell potential accurately as compared to the old voltmeters. So they are more advanced voltmeters now that will give you an accurate, closer to the actual cell potential. So the potential difference between the 2 electrodes is measured by using a potentiometer or a voltmeter, and the units are in joules, or in volts, sorry, in volts. That's the reason why on the batteries, those batteries that you put in your calculators, you see 1.5 volts. So 1.5 volts, that's the maximum amount of energy you can get from that cell. That's the maximum amount of energy you can get from that cell. For batteries, car batteries, so the total amount of energy you can get is about 12 volts. 12 volts, but now you can even go up to 24 volts. So each cell will give you a particular amount of energy. Now, that energy that it will give you will depend on the reactions going on in the cell, or the type of chemical reaction that's going on in the cell. Is it understood? Are there questions? Questions? Okay. So for measuring the L-nums, is it L-nums?
Yes, sir. I'm asking if you can use either a pointer or a sensor. I can't follow well.
You can't follow well.
I'm failing to understand because sometimes I even fail to follow.
You're even failing to follow. Okay.
Yeah, we are a lot.
You are a lot.
Yes, sir.
Almost everyone. Are we safe?
No, we
They
are
are
not.
not safe.
So we're not
Tem
safe.
fim tu essa.
You know,
Filetinha.
so of course this is not related to what we are doing now. But as a chemist, you have to be very imaginative So that's how we understand our like our chemical reactions. You have to put yourself in a chemical reaction and picture what's happening to each atom. So this is how this is moving, and this is how it attacks to that atom, and so on. Most of the concepts in chemistry, they are abstracts. So it's not something that's tangible that you can touch, but you just have to imagine, things, that this is what is happening. So the same way you imagine things in your life, I'll have a beautiful wife, I'll be rich, but you've never been there yet. So that's how you have to imagine the concepts in chemistry. All right, okay. So where do I get a point? Just a minute.
Simon, please make your mic, Simon.
Simon, please. Nijani,
Stop attacking Mr. Simon Well. Where is the point? As we grew up in the old days, we never had these gadgets. We are old-fashioned. Honestly, I can't find where the pointer is. I have to sit down, find time. I sit down, then start looking for these things.
You can use the same mouse, sir.
All right, sir, we can be following. Just
Yeah, you'll be following.
Just have a open read to the case, sir.
Okay. So you can see where the caser is now.
Yes, sir.
All right. Okay. Now we'll be fine. All right. Okay. So if you want to determine the amount of electricity that you get from the galvanic cell, you're using a voltmeter or a potentiometer. So I said a potentiometer will give you a more accurate cell potential than the voltmeter, because of in the voltmeter you lose part of the energy as heat. Now, if you construct a cell and you want to determine the voltage, or it will give you. So the cell potential, we call this cell potential. Now, the cell potential of a galvanic cell is just a sum of the cell potential of the half cells. Is the sum of the cell potential of the half cells. So when you look at this galvanic cell, right? So it's the voltage here, the cell potential is 0.76 volts. Now here you have one electrode is made from zinc metal. The other electrode is made from hydrogen, right? So it means here, they've shown the arrows for the arrow. You've seen the arrow for how the direction of flow of the electrons. So electrons are moving from zinc to hydrogen. to where hydrogen is. So which one is being reduced here, and which one is being oxidized between zinc and hydrogen? Yes,
Zinc is
zinc is being oxidized, right?
yes, sir.
Okay, so if zinc is being oxidized, then what do we call the half cell where zinc is?
It is the anode.
Anode. Okay, anode. And then for hydrogen, it's been reduced, right? So it's on the cathode, right? Okay. Yes.
Yes.
Now, in a galvanic cell, the anode, when you're writing a galvanic cell, the anode is always on your left hand side, and the cathode is always on your right hand side. So you have to remember that. Every time you are writing a galvanic cell, make sure your anode is on the left side and the cathode is on the right side. Then the charge also, the charge. So the anode is negatively charged and the cathode is positively charged.
The opposite side.
No, the reason why the cathode is positively charged is because electrons there, they are negatively charged, right? This is the easiest way to remember this. Electrons there, negatively charged. So the electrons are moving from the anode, which is negatively charged, to the cathode, which is positively charged. Because if they repel the electrons, because they are also negatively charged. Is that making sense?
Yes, sir.
Okay, yeah. So the cathode is positively charged, the anode is negatively charged. Now, in the electrolytic cell, the anode is negatively charged, is positively charged, and the cathode is negatively charged. So don't confuse the two. In a galvanic cell, the anode is negatively charged, the cathode is positively charged, because that's the only way negative electrons, they will go to the cathode because charged. But in the electrolytic cell, the cathode is positively charged and the anode is the cathode is negatively charged and the cathode is positive. The anode is positively charged. Okay. So these are some of the things that you have to know about the galvanic cell. And in a galvanic cell, electrons always move from the anode to the cathode, always. The reason why they are moving, it's because the cathode is positively charged. Okay. So if you want to find the cell here, so we are saying the cell potential is equal to, or is the sum of the half cells, right? So the anode and the cathode. So we just getting the cell potential for each element. So the element on the anode is zinc. What's the cell potential or the reduction potential for zinc? What's the reduction potential for zinc? Then the element on the cathode is hydrogen. So what's the reduction potential for hydrogen? Now, where do we get the reduction potentials for these elements? So the reduction potentials are here for all the elements on the periodic table. We have their reduction potentials. So you just come to the table here. Then you check where zinc is. So where is zinc? Zinc is somewhere here. Can you see where I've highlighted? Yellow.
Yes, I can see.
Okay.
Yes.
Yes, sir.
The reduction potential for zinc is negative 0.76, right?
Yes, sir.
Yes.
Then we go to hydrogen. Where is hydrogen? Where is hydrogen? Hydrogen is here. Hydrogen is here, right?
Yes, sir.
You've seen where I've highlighted the reduction potential.
0.00.
0.0, right? Okay. So we are saying we add the reduction potentials, right? So we are going to add the reduction potential for zinc. So our cell potential for this cell will be equal to reduction potential (76), then plus 0.00, right? So this will give us negative 0.776. When we go back to our cell,
So, sir, I have a question, sir.
sure,
Uh,
you can ask.
like for example,
If-
like for the reduction potentials, are
yes.
they given in a question, or you just have to know them?
Okay, that's a good question. So for electrochemical reactions, questions will give you the reduction potential. We'll give you the table. These are standards. So we'll give you this standard table. So you just choose the elements.
Okay.
Yes,
Yeah.
and also
Quite
they are on the
official.
same table which you just showed.
Sorry?
And also that table you just showed, hydrogen appears twice. There's somewhere
Hydrogen.
where it is 00 where you highlighted, and somewhere down. There's somewhere where it's negative 2.22 something.
Negative 2.22. Okay. Where is the table? Okay, so I'll also show you how to get the reduction potentials. Okay, so we have here also, right?
Yes. Now, how can we know which one to use?
Okay, so have you seen what's happening here? So you have hydrogen as electrons, metal, a neutral hydrogen metal that has gained 2 electrons to form hydride, right? Hydride is an ion. Then you have hydrogen ion that has gained an electron to become hydrogen gas or hydrogen element. The difference is this hydride here is an ion. It's not an element. The hydrogen here where there is 0, 0, it's you started with an ion, and then this ion is reduced to a neutral element. Look at zinc. So zinc was an ion this side, right? After gaining electron,
Yeah, I
it
understand
became
now. I get it.
zinc. Okay. Thank
No, sir, you can explain more.
you. Okay, yes, and the owner of the question has understood. Okay, so when you look at most of the elements that have been reduced here, they are going to the neutral state. They are all of them. They are going to the almost neutral metal. But the other one is becoming an ion. Okay. So when you look at sure, ask.
Can I ask if you can explain the difference between hydrogen down and that hydrogen up then?
So for the hydrogen, okay, mute. You should mute your mic. Okay, because I'm getting a feedback. Okay, so the hydrogen on top, you're starting with the hydrogen ions, right? Then this hydrogen ion is gaining an electron and becoming neutral hydrogen. That's what we want. The other hydrogen, you have a neutral hydrogen, it gains an electron and becomes the hydride, which is an ion. So it's reduction, but the type of reduction is different. Because in a redox reaction, what you have is metals, they are losing electrons, becoming ions. Then those that are becoming are gaining electrons, they are moving from being ions to being neutral metals, because they are gaining electrons. The other one, instead of becoming a neutral atom, it's becoming an ion also. So it has more electrons than the protons that are there. Now, I'll explain more on how to get these reduction potentials for each element. But what I wanted to show you was, have you seen the reading on the voltmeter? The voltmeter is 0.76 volts, but the sum gave us a negative 0.76. So where has the negative gone? Do you expect to have to see a negative reading on the voltmeter?
No.
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 Yeah, so it means when you construct a galvanic cell using from zinc and hydrogen, the amount of energy that you are going to get, or the voltage that you are going to get, or the amount of electricity that you get will be equal to 0.76 volts. So this cell will give you 0.76 volts. If we let's get another element. What elements would you want us to use? Let's go to the table. So let's construct a galvanic cell from any of these elements. Let's pick 2 elements.
Sir, a question.
Sure, go ahead.
Why are some values positive, others negative?
Okay. Okay. So I will explain. I'll explain that. Okay. So let's pick. You can pick two elements that we can use for constructing a galvanic cell.
Copper and hydrogen.
Copper. Copper. So where is copper?
Right on top of hydrogen.
Right in top of hydrogen. Okay. So we have copper. Okay. So the reduction potential is 0.16, right? Volts. Then hydrogen, it's 0.00, right? So the cell potential for this cell, if we construct it using copper and hydrogen, it will be the cell potential for the reduction potential for copper plus reduction potential for hydrogen. So it will be 0.16 plus 0.00. So this will give us 0.16 volts, right? Okay, so that would be the cell potential. Now, here, remember when I said that the amount of electricity that you get from the galvanic cell would depend on the nature of the reacting species, right? So it would depend on the amount of electrons that are shared between, or that are transferred between the two elements or in the reaction. Now, if we get the same copper, which just lost one electron, and the other copper on top, which is losing 2 electrons, the voltage will be 0.34. So it will be higher as compared to the other one, but they are both copper. The only difference is the amount of electrons that have been transferred. So the more the electrons are transferred, the higher the voltage that you are going to get. So the more reactive the metals are, the more reactive the chemical reaction is, or the more electrons are transferred in a chemical reaction, the higher the voltage that you are going to get. Okay, now where do we get these reduction potentials? So where do we get these reduction potentials? Of course, we have them on the standard table, but how did they get these reduction potentials for each element? So what they did was they constructed a galvanic cell. They constructed a galvanic cell, and then they went on the periodic table. Now, remember the reactivity series in what was it, grade 12? So you had metals from I think sodium going down up to I think copper somewhere there. So as you go down the reactivity series, the reactivity of the metals was reducing, right? Then you had the hydrogen. Then immediately after hydrogen, you had the elements that were less reactive. And above hydrogen, you have elements that were more reactive. So what they did was they got hydrogen and assigned it a reduction potential of 0.00 volts. And then they measured the reduction potential of all the other elements with the reference to the hydrogen reduction potential. So the reduction potential for hydrogen is sometimes called She, which is the standard hydrogen cell potential or electrode, the standard hydrogen electrode. Now, the standard hydrogen electrode or cell potential or reduction potential is 0. So elements that are less reactive like than hydrogen, they have positive reduction potentials. Elements that are more reactive than hydrogen, they have negative reduction potentials in most cases. So now what it means is, if I connect a metal to hydrogen, if the metal loses electron to hydrogen, it means hydrogen is less reactive than that metal. If I connect a metal with the hydrogen, if hydrogen loses electrons to that metal, it means that metal is less reactive than hydrogen.